ਅੱਜ ਦੇ ਐਪੀਸੋਡ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਅਸੀਂ ਉਹਨਾਂ ਆਰਗੈਨਿਕ ਕੰਪਾਊਂਡਸ ਬਾਰੇ ਜਾਣਾਂਗੇ ਜਿਨ੍ਹਾਂ ਵਿੱਚ C ਡਬਲ ਬੌਂਡ O ਫੰਕਸ਼ਨਲ ਗਰੁੱਪ ਹੁੰਦਾ ਹੈ। C ਡਬਲ ਬੌਂਡ O ਫੰਕਸ਼ਨਲ ਗਰੁੱਪ ਨੂੰ ਕਾਰਬੋਨਿਲ ਗਰੁੱਪ ਜਾਂ ਆਕਸੋ ਗਰੁੱਪ ਦੇ ਨਾਂ ਨਾਲ ਜਾਣਿਆ ਜਾਂਦਾ ਹੈ, ਜੋ ਆਰਗੈਨਿਕ ਕੈਮਿਸਟਰੀ ਦਾ ਇੱਕ ਬਹੁਤ ਇੰਪੋਰਟੈਂਟ ਫੰਕਸ਼ਨਲ ਗਰੁੱਪ ਹੈ। ਐਲਡੀਹਾਈਡਸ ਅਤੇ ਕੀਟੋਨਸ ਦਾ ਜਨਰਲ ਫਾਰਮੂਲਾ CnH2NO ਹੈ ਅਤੇ ਦੋਨੋਂ ਵਿੱਚ oxo group ਹੁੰਦੇ ਹਨ। The electronic structure of carbonyl group is as shown on the screen. In aldehydes, the carbonyl group is attached to one hydrogen atom and one alkyl or aryl group, whereas in ketones, it is attached to both alkyl or aryl groups. The functional group of aldehydes, as shown on the screen, that is CHO, is also called aldehyde group, while the functional group of ketones, that is C double bond O, as shown on the screen, is called ketonic group.
Before studying further, let us discuss the structure of carbonyl group. The carbonyl carbon atom is sp2 hybridized and forms 3 sigma bonds. The carbonyl carbon 1 sp2 hybrid orbital forms sigma bond with one half-filled orbital of oxygen atom, and 2 sp2 hybrid orbitals of carbonyl carbon forms 2 sigma bonds either with half-filled 1s orbital of hydrogen atom and half-filled orbitals of carbon atom, or half-filled orbital of 2 carbon atoms, depending upon the carbonyl compound. The fourth valence electron of carbon remains in its unhybridized p orbital and forms a pi bond by sidewise overlap with half-filled p orbital of oxygen. In addition, the oxygen atom also has 2 non-bonding electron pairs. Thus, the carbonyl carbon and the 3 atoms attached to it lie in the same plane, and the pi electron cloud is above and below this plane. The bond angles are approximately 120 degrees, as expected of a trigonal coplanar structure as shown in the figure.
The carbon-oxygen double bond is polarized due to higher electronegativity of oxygen relative to carbon. The oxygen atom carries a partial negative charge and the carbon atom a partial positive charge. These partial charges result in dipole interactions between molecules. This dipole interaction causes ketones and aldehydes to have higher boiling points than nonpolar alkanes of comparable molecular weight. Students, look at the table showing boiling point of butane is 309 Kelvin. The boiling point of propane 1-ol is 371 Kelvin, propanol is 322 Kelvin, and propanone is 329 Kelvin. Propanone and propanol have lower boiling points than to propane 1-ol of comparable molecular weight. Alcohols can form intermolecular hydrogen bonding, resulting in stronger intermolecular forces and relatively higher boiling points than aldehydes, and ketones boiling point of propanol is slightly less than propanone because dipole moment of propanol is slightly less than propanone. Children, let us now discuss general methods of preparation of aldehydes and ketones. Let us discuss the first method of preparation of aldehydes and ketones from alcohols. The first method of preparation, that is by oxidation of alcohols. Aldehydes can be prepared by the oxidation of primary alcohols with normal oxidizing agents such as acidified potassium dichromate or aqueous or alkaline potassium permanganate or chromium oxide and sulfuric acid. Let us have a look at the equation on the screen.
Primary alcohol on oxidation with potassium dichromate and sulfuric acid gives aldehyde and water. Let us explain this with the help of a specific example. Ethyl alcohol on oxidation in the presence of potassium dichromate and sulfuric acid gives acetaldehyde and water.
Aldehydes readily undergo oxidation to carboxylic acids. Therefore, to prevent further oxidation of aldehydes, these are distilled off as soon as these are formed. The yield of aldehydes is usually low by this method. The alcohols can be converted to aldehydes stage by treating with oxidizing agent pyridinium chlorochromate, that is C5H5NH positive, CrO3Cl negative. It is abbreviated as PCC. This reagent is used in non-aqueous solvents like dichloromethane, that is CH2Cl2.
Heptane 1-ol on oxidation with PCC in the presence of dichloromethane solvent gives heptanyl. Ketones can be prepared by the oxidation of secondary alcohols with similar oxidizing agents. Isopropyl alcohol on oxidation in the presence of potassium dichromate and sulfuric acid gives acetone and water. Let us have a look at another equation. Cyclohex 2-in-1-ol on oxidation with oxidizing agent PCC in dichloromethane solvent gives cyclohex 2-in-1-one. Children, aldehydes and ketones can be prepared by the catalytic dehydrogenation of alcohols. It is carried out by passing the vapor of alcohol over reduced copper at 573 Kelvin. When vapors of primary alcohols are passed over heated copper at 573 Kelvin, give aldehydes. Similarly, when vapors of secondary alcohol are passed over heated copper at 573 Kelvin, ketone is formed along with hydrogen. Let us take another example. When vapors of ethyl alcohol are passed over reduced copper at 573 Kelvin, acetaldehyde is formed along with hydrogen. 2-propanol, that is isopropyl alcohol, gets dehydrogenated to propanone in the presence of reduced copper at 573 Kelvin. Tertiary alcohols cannot be dehydrogenated to get aldehydes or ketones because they do not have alpha hydrogen with copper at 573 Kelvin. They get dehydrated to form an alkene.
Let us now learn about the second method, that is from carboxylic acids. Aldehydes and ketones can be prepared by catalytic decomposition of carboxylic acids. This can be done by heating a mixture of methanoic acid or other acids to 573 Kelvin in the presence of manganese oxide, that is MnO, which acts as a catalyst. On passing the vapors of methanoic acid over manganese oxide at 573 Kelvin, methanol is formed along with water and carbon dioxide. Ketones can be prepared by passing the vapor of fatty acids over manganese oxide MnO at 573 Kelvin. Fatty acids other than methanoic acid must be used. By passing acetic acid vapors over manganese oxide at 573 Kelvin, acetone water and carbon dioxide are formed. Children, let us now discuss the method of preparation of aldehydes and ketones by the dry distillation of calcium salt of acids. Aldehydes and ketones can also be prepared by distilling the calcium salts of the acids. Calcium formate, when distilled, forms formaldehyde and calcium carbonate. Calcium acetate, when distilled, forms acetone along with calcium carbonate. Let us now learn about the third method, that is from acid chlorides. Acid chlorides are converted into aldehydes by catalytic hydrogenation in the presence of palladium catalyst supported over barium sulfate. The catalytic mixture is poisoned by the addition of a small amount of sulfur or quinoline. This reaction is known as Rosenmund's reduction. Acetyl chloride, on catalytic hydrogenation in the presence of palladium catalyst supported over barium sulfate along with small amount of sulfur, gives acetaldehyde. Ketones can be prepared from acid chlorides by treating with dialkyl cadmium. The dialkyl cadmium needed for this purpose is prepared by the reaction between Grignard reagent and anhydrous cadmium chloride. Methyl magnesium bromide or Grignard reagent reacts with cadmium chloride to give the dimethyl cadmium. Acetyl chloride reacts with dimethyl cadmium in presence of dry ether to give acetone and cadmium chloride. Grignard reagent, that is RMGX, cannot be used in place of dialkyl cadmium. This is because the ketone formed would further react with Grignard reagent to give a tertiary alcohol. Ketones are prepared from acid chlorides by reacting with lithium organocuprates. Acid chloride reacts with dialkyl lithium cuprate to form ketone, cuprous chloride and lithium chloride.
Preparation of ketones from alkyl or aryl lithium. Ketones can be prepared by reacting acids with alkyl or aryl lithium followed by hydrolysis. Propionic acid on treatment with methyl lithium forms addition compound which upon hydrolysis gives unstable compound which loses water molecule to form butanone. Let us now learn about preparation of aldehydes from Grignard's reagent. Aldehydes and ketones can be prepared by the reaction of Grignard reagents on hydrocyanic acid or alkane nitriles, followed by acid hydrolysis of the addition product formed. Hydrocyanic acid on treatment with methyl magnesium bromide in presence of dry ether gives an addition product, which on hydrolysis gives acetaldehyde, ammonia and hydroxymagnesium bromide. Similarly, we find that acetonitrile on treatment with ethyl magnesium bromide in dry ether gives an addition product, which upon hydrolysis gives butane 2-one, ammonia and hydroxymagnesium bromide. We will now learn about the fifth method, that is, reduction of alkyl cyanides, Stephen's reaction. Alkyl cyanide, when reduced with stannous chloride and hydrochloric acid, gives addition product, which upon hydrolysis gives alkenyl. This reaction is known as Stephen's reaction. Let me tell you that ketones cannot be prepared by this method.
Children, we will now learn about preparation of aldehydes by hydration of alkynes. Aldehydes and ketones can be prepared by the hydration of alkynes in the presence of dilute sulfuric acid and mercuric sulfate as catalyst. Water adds to alkynes to form unstable enol intermediates which tautomerizes to form aldehydes or ketones.
Acetylene gets hydrated in the presence of a mixture of 40% dilute sulfuric acid and 1% mercuric sulfate to vinyl alcohol, which is an intermediate and which tautomerizes to a more stable compound, that is, acetaldehyde. Hydration of alkynes other than acetylene gives ketones. Propyne gets hydrated in the presence of a mixture of 40% dilute sulfuric acid and 1% mercuric sulfate to prop1 in 2-ol, which is unstable and which tautomerizes to a more stable compound called acetone. Next is hydroboration oxidation reaction. Alkynes can be converted into aldehydes and ketones by hydroboration oxidation reaction. Borane, that is BH3, or substituted borane compounds, that is RBH2 or R2BH, are used to give anti-Markovnikov addition of one equivalent of water, that is as a H and an OH to alkynes. Here R in R2BH is secondary isoamyl group. A hindered boron compound such as disecondary isoamyl borane, also called diisoamyl borane, reacts with an alkyne to give the mono addition product. This mono addition product contains a carbon-carbon double bond that could react with another molecule of disecondary isoamyl borane. However, steric hindrance between bulky diborane and a mono addition product A prevents the addition of a second molecule of disecondary isoamyl borane. When the initially formed boron compound A reacts with aqueous basic hydrogen peroxide, the Br2 is replaced by a hydroxyl group. The resulting hydroxyalkene, called an enol, tautomerizes to the corresponding aldehyde. Hydroboration of pent1-ine with diisoamyl borane and followed by alkaline hydrolysis gives pentenyl. hydroboration oxidation reaction of non-terminal alkynes forms ketones. But2-ine reacts with borane in the presence of tetrahydrofuran, forms intermediate, which upon oxidation forms enol. Enol tautomerizes to form butanone. Let us now learn preparation of formaldehyde from alkenes. Alkenes react with ozone to form ozonide, which on subsequent cleavage with zinc dust and water gives aldehydes and ketones. Ethylene forms ozonide with ozone in an inert solvent carbon tetrachloride. The ozonide are cleaved by zinc dust and water to give 2 molecules of formaldehyde. 2-methyl-but2-ene reacts with ozone in an inert solvent carbon tetrachloride to form ozonide. The ozonide is cleaved by zinc, dust and water to form ethanol and propanone. We will now learn about the Wacker's process. Alkenes can be converted to aldehydes and ketones by treating with an acidified aqueous solution of palladium chloride and cupric chloride. This method is called Wacker's process. Ethylene reacts with aqueous solution containing palladium chloride and cupric chloride to give acetaldehyde, palladium and hydrochloric acid as shown on the screen. Propene reacts with aqueous solution containing palladium chloride and cupric chloride to give acetone. Next is preparation of aldehydes by oxo process. Vapors of ethylene and water gas, that is CO plus H2, are passed over oxo catalyst, which is octacarbonyl dicobalt, at high temperature and pressure to form propion aldehyde. Next, we will discuss preparation of aromatic aldehydes from toluene. Toluene on oxidation with chromium trioxide dissolved in acetic anhydride forms benzylidene diacetate, which is isolated and is hydrolyzed with alkali to yield benzaldehyde along with acetic acid. We will now learn about the Itard reaction. Toluene can also be oxidized with a solution of chromyl chloride, that is CrO2Cl2, in carbon tetrachloride or carbon disulfide. An intermediate A brown complex is formed, which is decomposed by water to give benzaldehyde. This reaction is called Itard reaction.
Children, we will now learn about preparation of aromatic aldehydes from phenols. Salicylaldehyde is obtained by treating the phenol with chloroform in aqueous sodium hydroxide solution at about 343 Kelvin. This reaction is called Reamer-Tiemann reaction. We will next learn about formation of benzaldehyde by Gattermann Koch reaction. Benzene on treatment with carbon monoxide and hydrogen chloride in the presence of anhydrous aluminum chloride and cuprous chloride acting as catalyst is converted to benzaldehyde. Next we will discuss preparation of aromatic ketones from benzene by Friedel-Crafts reaction. Benzene reacts with acetyl chloride in the presence of anhydrous aluminum chloride and forms acetophenone.
The carbonyl group undergoes many types of reactions, including nucleophilic addition substitution, oxidation, and reduction reactions. Now we will discuss the relative reactivities of aldehydes and ketones in nucleophilic addition reactions. Students, aliphatic aldehydes tend to be more chemically reactive than aliphatic ketones for two principal reasons. The carbonyl carbon atom in aliphatic ketones is more sterically hindered from nucleophilic attack than is the carbonyl group of an aldehyde. Compare structure 1 with structure 3 as shown here. Circles represent the van der Waals radii and electron clouds. The tetrahedral intermediate resulting from the addition of the nucleophile is more sterically strained, has higher potential energy for a ketone, as shown in structure 2, than for an aldehyde, as shown in structure 4. Secondly, aliphatic aldehydes has one alkyl group due to its electron-releasing inductive effect, that is, plus I effect. It tends to increase the electron density on the carbonyl carbon atom, but aliphatic ketones have two alkyl groups. It increases more negative charge on carbonyl carbon due to plus I effect of two alkyl groups. Thus, two alkyl groups in aliphatic ketones decreases the positive charge on carbonyl carbon more than carbonyl carbon of aliphatic aldehydes, and thus ketones are less reactive than aliphatic aldehydes. Aromatic aldehydes are less reactive than aliphatic aldehydes and ketones. This is attributed to the conjugation effect, which is present in the pi electrons of the ring and in the carbonyl group. This is also termed as -M effect of the carbonyl group. Aromatic aldehydes are more stable, that is, less reactive, than alkyl aldehydes towards nucleophilic addition because of resonance stabilization. The positive charge on the carbonyl carbon atom can be shared with the benzene ring as shown by the resonance stabilized structures. Since the positive charge is spread throughout the molecule, the positive charge on the carbonyl carbon atom is reduced. The lower partial positive charge on the carbon atom decreases the attraction towards an attacking nucleophile. Now that we have learned so much, let me ask you a few questions. My first question is, how can we convert cyclohexanol to cyclohexanone? And the answer is, cyclohexanol on oxidation with oxidizing agent, potassium dichromate and sulfuric acid gives cyclohexanone. The next question is, How will you convert an alkene into an aldehyde containing one carbon atom more? And the answer is, it can be done by oxo process, in which vapors of water gas and alkene are passed over oxocatalyst, that is octacarbonyl dicobalt.
ਬੱਚਿਓ ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। ਥੈਂਕ ਯੂ ਫॉर योर काइंड अटेंशन। See you next time.